Hello everyone, welcome back to a brand new video. Today we're going to be looking at this disgusting looking integral. I don't even know what I've come across here, but I saw this posted online somewhere and I thought I would give it a go, and I got the solution to it. It's actually not too bad. It involves some series expansion. That's the sort of the method here, the key to unlocking this integral basically. So well, what have we got? We've got the integral from 0 to infinity of 1 minus e to the negative ax, where a is some number, times all times by e to the negative x over x dx. Okay, so it took me a while. I managed to get there in the end. And the way we're going to do it is, of course, as I just mentioned, using series expansion. And more specifically, the series expansion for this term right here, e to the negative ax. So let's recall our series expansion for e to the power of x. So e to the power of x is just, let me, hang on a minute, it is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4 over 4 factorial. That is, and so on, I should say, all the way off into infinity. And that comes about because this is equal to the sum from r is equal to 0 up to infinity of r factorial, and I think it's just x to the r. I believe that's the case. Yes, yes it is. That is the series expansion for e to the x. Thank you, Taylor Swift. Of course, we have to give her props for this. Yeah, this is the Taylor series expansion for e to the x. Thank you, Taylor Swift. So, well, we don't have e to the x, though. We have e to the negative ax. Well, that's good, because all we have to do is just go ahead and replace all of our x terms in this expansion with negative ax. So that's going to look like 1 plus negative ax plus negative ax squared over 2 factorial plus negative ax cubed over 3 factorial plus negative ax to the 4 over 4 factorial, and so on off into infinity. Okay, let's sort of tidy it up a little bit. So we're going to have e to the negative ax is equal to 1, and this next bit's going to be minus ax, and then we've got negative ax squared, so that's going to be plus a squared x squared over 2 factorial. Negative ax cubed is going to be minus a cubed x cubed over 3 factorial. And then to the power of 4, so we're going to have plus a to the 4 x to the 4 over 4 factorial minus, and so on, off into infinity. We're going to have infinitely many terms. Well, let's condense this a little bit, and let's go ahead now and write this as a sum. So we've got e to the negative ax is equal to the sum from r is equal to 0. Actually, I don't like using r. I'm going to use the letter n. N is equal to 0, all the way off into infinity, of negative ax to the power of n over n factorial. Okay, brilliant. So we can go ahead and replace that in our integral now. So we've got, we've just expanded e to the negative ax. So we're going to have the integral from 0 to infinity of 1 minus the sum from n is 0 to infinity of negative ax to the power of n over n factorial times e to the negative x over x dx. Now, you're probably wondering, well, hasn't this just made it more difficult? Haven't we just made it harder for ourselves? Well, let's tidy some things up a bit here. As you can see, the expansion for e to the negative ax, it's the first term was 1. And so if we've got if I highlight it, if we've got 1 minus this entire thing, well, that's saying 1 minus and then 1 minus ax and so on and so forth. And so this one right here and this one are going to cancel out completely. And so this reduces to the integral from 0 to infinity of negative the sum from n is 0 to infinity of negative ax to the power of n over n factorial times e to the negative x over x dx. Okay, and well, where do we go from here? Well, again, we can actually tidy up a little bit more. Let's go ahead and sort out the sum. It's in a certain form at the moment, but we've got sort of a mixture of x's in our integral here. Let's see if we can combine them in some way. So we're going to have the integral from 0 to infinity of the negative sum from n is 0 to infinity of, well, negative a to the power of n times x to the power of n over n factorial times e to the negative x over x dx. So all I've done there is split up these brackets here. And now what we can do is go ahead and divide by this x. So we've got x to the power of n in the numerator, we've got a single power of x in the denominator. So using our laws of indices, this reduces to the integral from 0 to infinity of negative the sum from n is 0 to infinity. Oh, my bad. I've just spotted something. I'm sorry if you spotted this already. But when we got rid of this 1 right here, when we did 1 minus this sum, our sum no longer starts from the n is 0 position. This is n is 0, this is n is 1, this is n is 2. Because we got rid of the n is 0 position, our sum now starts from n is 1. I do apologise if you saw that. That must have been quite frustrating. So let's go ahead and correct that. So it's actually the sum from n is 1 now. We've sort of re-indexed it a little bit. Okay, well, this is going to be negative a to the power of n, x to the n minus 1 now, over n factorial times e to the negative x dx. Okay, we're almost there. We're almost there. We've almost got it in a form that is usable. So we're now going to simplify it even more. Well, okay, so if we go ahead then and try and integrate this. Okay, so how can we go ahead and do this? Well, I'm going to group together this x to the n minus 1 and this e to the x now. So we can write this as the negative sum from n is equal to 1 to infinity of negative a to the power of n over n factorial times x to the n minus 1 times e to the negative x dx. Now, we've got this integral now, and so it's the integral in terms of x with respect to x, and, well, our only x terms are right here. So what is this term, these terms right here, sorry, but a constant? And so we can bring them out to the front. Excellent. So we've got the negative sum from n is 1 to infinity of negative a n over n factorial times the integral from 0 to infinity of x to the n minus 1 e to the negative x dx. Brilliant. We've now got an integral to solve. We can go ahead and find this integral right here. And also I should say that I is equal to this integral. So let's deal with this integral now. So we're solving the integral from 0 to infinity of x to the n minus 1 e to the negative x dx. Well, hopefully you can spot this is going to be integration by parts. So we've got u being equal to x to the n minus 1, which implies that the derivative of u is equal to n minus 1 x to the n minus 2. We're going to have v dash equal, so the derivative of v equal to e to the negative x, and v therefore equal to negative e to the negative x. And so if we apply the integration by parts formula, which is uv minus the integral of v du dx, we're going to get u times v, which is going to give us negative e to the negative x, x to the n minus 1 evaluated from 0 to infinity, minus the integral from 0 to infinity of v du dx, so this times this. So we're going to get, well, that's going to become a positive. We're going to have n minus 1 x to the n minus 2 e to the negative x dx. Okay, so what's gone on here then? Let's define this integral to be the integral from, to be I of n. So if this is I of n, yeah, that's fine. So I of n is equal to this integral. And I'll show you why we've done that. We've called it I of n. So if I just rewrite this, so we can bring this n minus 1 to the front, because that is, of course, just a constant. So we've got plus n minus 1 times the integral from 0 to infinity of x n minus 2 e to the negative x dx. Well, we have got right here a integral that is very, 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 very close to the integral we started with. The only difference is the power of the x here. It went from an n minus 1 to an n minus 2. And so, if we've called our integral, if we've called this integral I of n, then this new integral that we've got is, well, it's just n take away 1. So this right here is going to be I of n minus 1. Excellent. So we've got minus minus e to the power of minus x, x to the n minus 1, from 0 to infinity, plus n minus 1 times I of n minus 1, like that. And I'll show you why that's important to recognize that. So, in fact, I'll go ahead and do it, actually. We're going to do integration by parts again. So we know that this is equal to I of n minus 1, okay? But let's go ahead and do integration by parts again. So we're going to say u is equal to x to the n minus 2, v dash is equal to e to the negative x. So that implies the derivative of u is equal to n minus 2 x to the n minus 2, and v is equal to negative e to the negative x. So therefore we're going to have u times v minus the integral of v times du again. So we're going to have negative e to the negative x, x to the n minus 2, minus the integral from 0 to infinity of v times du dx. So that's going to become a plus n minus 2 comes out the front, x to the, oh, that should be n minus 3 as well, my bad, x to the n minus 3, e to the negative x dx. Right, and this pattern is going to keep on decreasing. We're going to keep on, what's the word? It's going to keep on occurring, because this is just I of n minus 2. This was I of n minus 1 up here, and so we've got I of n minus 2 down here. So let's just quickly rewrite what we've got so far. So if I zoom out really quick, we've got negative e to the negative x, x to the n minus 1 from 0 to infinity, plus n minus 1 times by negative e to the negative x, x n minus 2, evaluated from 0 to infinity, plus n minus 2, the integral from 0 to infinity of x to the n minus 3, e to the negative x dx. That's what we've got so far. Okay, let's see what, let's evaluate this term right here. So negative e to the negative x, x to the n minus 1. Well, let's see what happens as when we evaluate this as the limit approaches infinity. So let's say that this is equal to negative e to the negative x, x of n minus 1 from 0 to t, and it's going to be the limit as t approaches infinity. Well, let's see what happens. So we're going to get negative e to the negative t times t to the power of n minus 1. minus, we're going to have negative e to the 0 times 0. So that whole thing goes to 0. So we've only got this right here. We've got negative e to the negative t to the n minus 1, and this is as the limit of t goes to infinity. Okay, so let's see what happens. So as t approaches infinity, well, what's going to happen to this? Well, let's rewrite this, and let's write this as negative t n minus 1 over e to the t. And as you hopefully know, as t approaches infinity, e to the t is going to approach, e to the negative t is going to approach 0 because e to the t approaches infinity. And so if you take the reciprocal of that, you're going to get 0. So that means then that this entire thing approaches 0. So we can replace this with 0 essentially. So every time we see a negative e to the negative x to the power of anything evaluated from 0 to infinity, we're going to replace that with a 0. So let's rewrite what we have got so far. If I quickly just zoom out. Okay, so we are going to have this first term here being, of course, 0. I'm going to write it here. We're adding n minus 1 times by this term right here, which we've said evaluates to 0, plus n minus 2 times, and then the pattern is going to keep increasing because all we're doing is we're doing the same integral over and over and over again, but the n is, or the power of x is decreasing by 1 each time. So we're going to have 0 plus n minus 3 times 0 plus n minus 4 all the way down to when that x no longer has a power, when n doesn't have a value. So let's go ahead and simplify this. So we can get rid of all of the zeros. So we're going to have n minus 1 times n minus 2 times n minus 3 times n minus 4 all the way down to when we get to 0. Or, sorry, not 0, 1. All the way down to when we get to 1. Okay, so, well, what is this? This is n minus 1 factorial. Great, okay. I should point out as well, at the very end of our sort of chain here, we're going to have I of 1, the integral I of 1 right at the very end. But if we recall back, we said I of n was equal to this. So that implies that I of 1 is going to equal to the integral from 0 to infinity of x to the 0 e to the negative x dx. X to the 0 is of course just 1. And this whole integral evaluates to equal 1. So this is going to equal 1. I of 1 is equal to 1. And so we're just timesing it by 1. So it's just equal to n minus 1 factorial. Great. We've just evaluated I of n, and we got n minus 1 factorial. Cool. So let's go back to the whole reason we were doing this in the first place, evaluating this integral right here. So we can actually go ahead and rewrite now what we've managed to get. So I'm just going to quickly move all this garbage out of the way. It's not garbage, it helped, doesn't it? Didn't it? I'll give it I'll give it some credit. Content outside of it, yeah, I don't care. Right, so we said that this was equal to n minus 1 factorial. Brilliant. So let's rewrite what we've got. We've got I is equal to negative the sum from n is 1 to infinity of negative a to the power of n over n factorial times n minus 1 factorial now. Amazing. Now we just need to work with this sum. And then we've got our answer. So I is equal to negative the integral, the sum from n is 1 to infinity of negative a to the power n. Now, what is n factorial if not just n times n minus 1 factorial? Right, so we can write n minus 1 factorial, and that n minus 1 factorial is of course at the top. And what happens? Well, they're gone. And so we've got I being equal to the negative sum from n is 1 to infinity of negative a to the power of n over n. And if you watched my previous video, don't blame, I do not blame you if you didn't. But anyway, if you watched the previous video, you know that this looks awfully familiar. This looks like the series expansion for ln of 1 plus x. If you recall, ln of 1 plus x can be written as the negative sum from n is 1 to infinity of negative x to the power of n over n. That's exactly what we've got here, and that means that this integral, this sum, sorry, is equal to ln of 1 plus a, because all we've done here is replace the x with an a. So we've reduced it down, and we've managed to get a sum that's the exact same as our ln of 1 plus x expansion. And so that means this sum is equal to ln of 1 plus a, which means I is equal to ln of 1 plus a. And I was our original integral, and so we can conclude that the integral from 0 to infinity of 1 minus e to the negative ax, e to the negative x, over x dx is equal to ln of 1 plus a. A nice general result. Thank you very much for watching.